Hello everyone, this is Hanzian Huang, a second-year PhD student from UC San Diego. I'm working with Professor Jishen Zhao. I'm very happy here to share my project on PIRL towards easier persistence-aware programming, a deep reinforcement learning approach, which aims helping translate volatile C or C++ source code into the corresponding persistent-aware codes. So this is the outline of today's presentation. First, I will talk about the motivation of this project. What is the difficulty in persist memory-aware programming, and why we want to ease this programming. And then I will show how the problem is defined. And I will show our solution, which is a reinforcement learning-based framework, and finally show the results. The motivation comes from the challenges in persistent-aware programming. We all know that the non-volatile memory enables fast and durable storage. The only concern is that it will suffer consistency problem after power failure. So it brings challenges for users to write additional codes to promise the consistency and enable the recovery after the system failure. The first challenge is that users need to learn additional program knowledge, such as one may need to be familiar with some non-volatile main memory-aware library, and also know knowledge on memory, such as how and when to flush the cache or add memory barriers. And the second problem is that it requires in-depth code changes based on the original volatile code, and it's very labor intensive. So some non-volatile main memory aware libraries and toolkits are developed to offer more higher level functions and enable a friendly programming method. However, users still need to study how to use this library or toolkits to do much additional programming. And the last challenge is that the additional coding easily leads to new errors, or it requires some expert experience to promise the correctness. So our goal is to close the gap between user and the persistent memory. How can we help a new user, assuming who only know how to do volatile programming, to have a correct persist-aware programming? So we want to assist automatic, correct, efficient, and fast persist-aware code generation. Here we show what is this problem looks like. Suppose the users only need how to write volatile C or C++ code, and the user also know which data structure wanted to be stored in the persist memory. So the input is a piece of pure C or C++ volatile source code and the assigned data structure. And the output is the corresponding persist memory-aware C or C++ code with the desired and safe control on the target data structure. And here's an example of the corresponding input source code and the target output code after adding some APIs. So in this black box, we firstly want to choose some correct programming APIs, such as this transaction begin, end, or add, etc. Actually, these APIs can be some high-level library interface, and also it can be also some low-level assembly codes or instructions. So here we choose the PMDK library APIs, which is more convenient in coding and also easier to do the checking. I manually collect some PMDK APIs from the PMDK example codes to be an API pool in the first step, especially some C++ binding APIs from the PMEM-object++ library, by which we can easily assign which data structure to be persistent. So after choosing the API, we need to insert it into a correct place. It can be insert one line of code or wrap a piece of code into an API. Here we will slice the source code by curly brackets. And after that, we need to use some checkers to check and promise the persistency and consistency of the generated program. Here we mainly use Evergreen PMEMCHECK and PM-Reorder. So here we show an example. Suppose the users have a volatile code like this, but want to put the list structure into persist memory. So when we need to do something, when we want to append the list, we need to do something. So each time we will pick one API from the API pool and insert it in some place. So for example, this time we will choose transaction begin and end and wrap a piece of code like these 3 lines of code into this transaction API, and then after each modification, actually we can say the code goes into a new code state from the original code to the code with this transaction begin and API. So after that, we will check the persistency and consistency with the checker of each new node and feedback each new state with a grade. And then we will pick another APIs and insert and modify the code and then check to do this iteration. Sometimes we may need to do backchecking and also update the grades of the precedent states and try new APIs from the precedent states. And after this iteration, we can finally come out a solution. So we use the multi-color tree search-based machine learning framework to search the proper modification of the program. Here I will first go through the multi-color tree search in a high level, and I will after that I will show the whole framework. So the multi-color tree search is basically a kind of a broad definition of a kind of tree search. So you can do it in a conventional way or combining with some machine learning neural network to help improve the policy and evaluation function. As shown in this figure, there are 2 elements in this tree, the node and the edge. So the node here represent different code states as the example we show above. So each node may have some different library API combinations based on the root nodes, based on the source code. And the edge means inserting an API in a certain place. It's a kind of action, and which will change the code states. Each state and each edge will have a edge value. We will call it a benefit value here to represent how good it is to take this action on the current node. The multi-color search combines 4 steps: selection, expansion, simulation, and backpropagation. The first step is the selection. So starting from a certain root, we will select the edge, which will maximizing the edge value plus the probability. And we will get the probability from a policy and value network. We choose to use the neural network, and yeah, we will introduce that later. And this step to choose the edge maximizing the edge value plus probability. So this step will actually reduce the search width by focusing on only exploring the high probability node. And the second step is the expansion. So after take certain action through the edge, we will change the code states from one node to another node. And the third step is simulation. So there are 2 parts in this simulation. The first part comes from the value network, and the second part comes from a random rollout to the leaf nodes using a default naive policy. So in this step, we will take the positive children nodes into consideration by this simulation. And the final step is to use the result of the rollout to update edge value along the path from current nodes to the root nodes. So why we implement this searching agent by multi-color tree search? Because it's an efficient search algorithm to solve the huge search space problem, and yeah, because we will train the policy network to focus on only exploring the high probability nodes, or say the high value nodes. And second, it's a kind of look ahead search. So it will take the rest of the actions, the rest of the possible nodes into consideration, and simulate the searching to update the current node. So after introducing the multi-color tree search, we will introduce the whole framework, which is a reinforcement learning-based framework. The framework consists of 3 stages. The first stage is observing the states and encoding the program into input into this policy and value network. And then in the second stage, the network will take action to choose and insert APIs in a certain place into the program, into the current program. And in the third stage, the environment, which is our persistency checker, will take the modified code as input and check the persistency and consistency and give some feedback to this network. So in the training process, the network will get this feedback, get this reward, and update its parameters according to this feedback and learn how to explore more reasonable actions to win more positive reward feedback. And yeah, that is the model learn how to modify the code based on the library and try to promise the persistency and consistency. And after we train this policy and value network offline, we can do the online inference. So in the inference stage, the well-trained neural network will imitate the human behavior of choosing and inserting API to help, and this step will help us modifying the program. Compared to other supervised learning neural network, we don't need to prepare too much data sets because we will have a simulation process to generate the data set along this process. Yeah, but if we actually have a well-prepared C++ and the corresponding golden persist memory-aware code pair dataset, we can also try supervised learning model. So here I only want to introduce our framework in a high level and skip the detail on of how to build or train this model. And in the experiment, we use Volgren PMEMCHEck and the PM-Reorder to evaluate the consistency and persistency of the generated program. So we use Volgren PMEMCHEck to validate the correctness of the stores that made into the persist memory, and also get the error numbers of not persistent stores from the report. And the PM-Reorder will check the code consistency by running different combination of several stores between flush fence barriers. So these are the datasets I use to train and test the model. So the training dataset comes from the C or C++ version of PMDK example code, and the test set is part of an open source LeetCode solution dataset. So here we show some experiment results of the proposed framework. The generated code from our framework on such as tree, hash, array, queue, structure, etc., micro benchmark, and also the real world case KV store, they can all pass the both Volgren PMEMCHECK and PM-Reorder test and shows persistency and consistency correct. So it means on these test cases, our model can achieve 100% translation accuracy. And we can also see from this figure that the generated code on microbenches have very similar average execution time of multiple reads and writes compared to the expert code. And we can also show an example later that the generated code on microbench is actually very similar to the expert code. And for the real world case, KV store, since the code has more complicated data structures and functions, so our generated code may lead into some redundant APIs that have higher overhead, but we can still promise the persistency and consistency correct in this case. Here I show an example of our generated code based on the Q data structure. So the input is the pop function of Q, and our framework will insert the transaction run and delete the persistent objects, and then we can finally get the right-hand side corresponding PM-aware code. And actually, this kind of translation is one of the efficient ways to make this pop function persist. As we have shown before, our translated code have very similar efficiency compared to the PMDK baseline code. And the code translation can actually be failed, especially in some complicated cases, since we all know that the machine learning is inherently fuzzy and approximates. So uh, I show some fail cases here. We can figure out that the fail cases can be like missing or wrong APIs, like inserting the API into a wrong place, or it can be successful on most of the parts, but fail on the other part of the code. So the whole piece of the code is failed. However, very luckily, most of these bugs can be easily detected by the checkers or debugging tools, so we can still fix the wrong parts by the debugging tools and make the whole piece of the code work. So we can say our framework can help towards easier PM-aware coding to some extent, and the generated code can actually be further improved by the checker or debugging tools. We are still trying to improve the code translation quality and try to make our framework more robust. So our model can be improved from this aspect. First, we will try to find more training datasets. The training dataset is the volatile source code and the corresponding golden PM-aware code pair. The better dataset will cover more cases, especially the real-world cases, so it can improve the model translation accuracy and also make our framework more practice. We are still trying to improve the code translation quality and also try to make our framework more robust. So our framework can be improved from this aspect. First, we would like to try to find more training datasets. The training datasets is the volatile source code and the corresponding PM-aware code pair, and the better dataset will cover more cases, especially the real-world cases, and it can improve the model translation accuracy and make our framework more practical. And second, we are currently only consider the code persistency and consistency. So we will further also consider the code efficiency in the reward function to award the higher efficiency generated code with a higher grade. So this can help reduce the redundant APIs and lower the overhead of the generated code. And third, we will use other additional checkers in training, and this can make our model to learn to how to avoid other kinds of bugs and make the generated code more robust. And finally, as we have mentioned before, we will use some debugging tools such as PM test to fix some syntax or performance bugs. So by doing all of this, we will further improve our framework and try to make it more practical. And finally, to summarize our work, we introduce a deep reinforcement learning approach to help ease the persistence-aware programming. Given the volatile source code input, our framework will generate the corresponding non-volatile-aware codes based on the PMDK library APIs, and the persistency and consistency will be checked by PMEMCHECK and PM-Reorder. We have shown successful translation on both microbench and real-world case, and our generated program can achieve similar performance compared to the experts code, especially on the microbenches. And the generated codes can be also further improved to reduce the syntax bugs and performance bugs by other debugging tools. And our work contributes to reduce the study costs and labor on modifying existing volatile datasets, and also encourage the use of non-volatile main memory on the existing volatile source code. All right, that's so much of my presentation. Any questions and suggestions are welcomed. Thank you for listening.